Yeah, like Tom mentioned, we're actually starting a new experiment on how we can exploit what is available in terms of global precipitation products. So, as we all know, they actually vary in different coverage of temporal coverage or different spatial resolutions. So actually, it's now a era of abundance of different models. So maybe we can combine all of them to obtain a one better model suitable for different regions. And also, lots of station data sets are available that can be merged together with the satellite-based information to reduce bias and possible artifacts, together with the other covariates that derives the precipitation changes in terms of spatial and temporal. But of course, the main ideology behind this was actually driven from the fact that we are actually excessively mapping properties 2000 and onward with the R&D Landsat data set we have. So it's the main purpose behind is to have a proper covariate that can be used for various types of modeling, but with, of course, less artifacts and problems. So far, we've been using Chelsea and some of the downscaled version of precipitation dataset, but we also suffer a lot of artifacts in our spatiotemporal modelings. So the starting point of our modeling was the GSOT dataset that is distributed by NASA and NOAA, sorry. And it's a global surface summary of the day, which means they actually summarize the couple of main climate covariates as a daily data set, which is actually a data set produced by an hourly data, integrated surface hourly data set, another data set also distributed by NOAA. And they distributed the data set 1930 plus and onward. But of course, the 1973 and onward is actually more proper and complete in terms of gaps. And there are nearly 20,000 stations globally, but of course you can see the distribution from the map. It's heavily dominated by the northern hemisphere, so the southern hemisphere also some areas are actually underrepresented in terms of station data coverage. So it also creates another problem in the modeling as well. Like I said, we are mostly concerned with 2000 and onward period. So that's why you see the distribution of the temporal coverage of these stations from 2000 to 2024. And I've also given a little chunk of data spaces between stations. So the space is also temporally, it's not quite homogeneous, of course, but when you look at the number of stations per year covered by GSOT stations, it's quite homogeneous actually after 2000 and onward, but before is actually much worse. So the area that we are interested is actually quite well covered in terms of that. But in our multi-fusion framework, at first we were also thinking about including maybe Chelsea dataset. So that's why we actually limited to until 2020, because that's the time Chelsea version actually stops. But we are looking for another solution, modeling without Chelsea, of course, and so that we can extend the dataset 2020 and onwards. And so this is more of the framework that we are working on, but of course the model and the modeling framework is will be definitely expanded and enhanced. But we are beginning with collecting the Area 5, iMerge, Terra Climate, Chelsea N, DTM covariates, and out of these, Area 5, iMerge, and Area 5 and iMerge are 10-kilometer data sets. Chelsea is 1 kilometer downscaled, and Terra Climate is 4 kilometer. And for a DTM, we are using the in-house DTM model that we have, GDTM, which was presented by Yufeng, if you were here yesterday. What we do is we are creating some covariates from these models, usually total precipitation to be fused, but also some other climate data sets from Terra Climate, which is 4 kilometer data set, like minimum, maximum temperature, soil moisture, which is also integrated part of the water cycle, and surface radiation and wind surface. And we are using the raw DTM heights along with a couple of derivatives of the DTM in a highest resolution possible. And together we are actually preparing these covariates for each stations, for each space and time to create the final training data set, for which we separated based on the number of stations. 90% of the station was used for training and 10% testing. We did also 80 and 20 testing. But of course, the number of stations to 20,000 is still not a lot to be able to significantly downscale the resolution. So that's why actually using more in the training, it actually is advantageous. But of course, it's subject to discussion, the portion of separation. But what we do is to be able to fare in the modeling, we do some sort of special blocking in the cross validation, where we create like 100 kilometer by 100 kilometer blocks. For each special blocking, for each training in the cross validation, there are no data sets in which the block actually contains one of the ground station. They are separated for the validation, and of course for the hyperparameter tuning, which is done by Bayesian approach with Optuna framework. And after the model is actually tuned, we do the final testing to do fair comparison with the ground data. So this is the correlation matrix for the covariates that we use. So you see, they are of course expectedly highly correlated with the satellite data sets. The PRCP is the ground observations precipitation, and they're followed with the satellite-based precipitation data sets with other climates. And at the bottom, you see the topographic features, which are less correlated with the precipitation, the monthly precipitation values. Of course, when you think about random forest, having extremely highly features is not quite advantageous. Of course, this is also subject to discussion for the future modeling. And the precipitation in terms of phenomena is actually quite zero inflated problem. So that's why having a lot of zero in the modeling is actually creating underrepresentation. So that's why we are changing the modeling space into log space when we are doing the modeling. But of course, when we are testing, we are switching to the real space back. As you see in the comparison of the histograms, the log space actually distributes the data towards the normal distribution a bit more rather than the real space. So this is the initial result you see in terms of log space, of course. But above we have the statistics both in log space and the original space. So the R value in real space is around 65, but of course the model is extremely dominated by Chelsea precipitation values, which is in fact also downscaled with the ground station. So that's why there's a bit of a circulation in the model. So we also this circulation actually causes the dumping effect towards the other precipitation datasets and also other covariates as well. So that's not actually a quite good or expected model that you would like to see. So when we remove the Chelsea from the modeling, actually the performance actually does not drop significantly. It's actually dropped only 1%, 3% in R-square value, but the correlation is still high compared to the previous one, 0.85 to 0.80. And in real space, it was 0.65, and now we have 0.63. So not a significant drop in the model performance, but of course, now the model can pick up the importance of other precipitation models and along with the other covariates you see. When we look at the time series in the real space, the model actually can generally pick up the trend and seasonality within time series. And at the right side, you see the comparison between our predictive model and also the Chelsea. So this model actually does not include Chelsea, so we can fairly compare the performance. And the mean value and median value is actually significantly improved compared to Chelsea, but still, I think there is a bit of a room for improvement. But of course, model is not sensitive to extreme values, and it actually underestimates in those values, and it's also subject to search. But to summarize the preliminary results, the model actually has 0.63 correlations, and it's doing better than Chelsea 1 kilometer model now. But of course, to be able to use these sort of models in the climate modeling as well, they need to be able to catch the extreme values. So that's a bit of a problem. And for that, actually, usually in literature, deep learning models actually doing much well in catching the extreme values, like convolutional values that can convolutional, or maybe also space-time models like convolutional LSTM, so that they can both capture spatial and also temporal patterns easily. But what we are interested in the most is also the uncertainties. So for that, we have in-house implementation of C++, quantile random forest. So we will first try this model, but of course, there are other models that can also derive uncertainties like GPR, but it's quite computationally heavy model. Actually, last night we started, but still running. So anytime soon we are expecting results. But of course, we don't have to model the whole space in terms of Gaussian process. We can of course reduce the complexity by doing sampling, but we are looking for a better approach to both capture the spatiotemporal patterns, but also create a realistic uncertainty outputs. So yeah, that's the summary of the modeling. Yeah. Thank you.
Okay, thank you, Serkan. Yeah, we have time for questions. You didn't try making predictions for some tiles, or not yet?
Not yet.
Okay, that's coming. But it's a good result. It's promising. So we can, with data fusion, basically you proved it, that we can produce a more accurate than the cutting edge 1 kilometer product. So that's a good, it's a good output of this project. And I think many groups need a, most accurate precipitation possible. What about this other point data set? There was this other data set I sent you, released on the.
Oh, that's the same. That's it. Just different temporal span.
Okay.
Yeah. So that's
included. There was a paper which has a precipitation
data
network
from scientific data. Yes.
Okay.
Yeah.
So that's included also.
That's included.
Okay.
Yeah.
Yes, here, Felix.
Thanks, Serkan, for the presentation. I have a question regarding the splitting of the data, like the train test and then the spatial blocking within the training data. Did you, like the initial train test split, did you also do it like spatially blocked, or was this done like randomly?
No, the 10% of the number of station was also separated like a blocking, so that there were no over selection in the same block again and again. So it's also a possibility.
Also with the 100 kilometer.
Yes.
Okay.
Yeah.
Thanks.
You need to put that in the plot also, so people see.
Yeah, but also
there's a question in the back here. Luca, please. First, Luca. Luca, go for it.
Paolo is my. I have actually two questions. The first is why monthly and not daily, since IMER, Gira5 are all available at daily scale. And the second is if you have tried to use this precipitation product as forcing for hydrological model.
Can you repeat the second question again?
If use this precipitation product as a forcing in hydrological models to estimate the discharge.
Okay, that's a good question. The first one, the reason actually we are actually modeling monthly is it's not does not have an answer in a hydrological sense, but actually, like I said in the beginning, it was this project was to support our in-house modeling. So that's for that we need monthly product, and that's the actually initial point. But we were thinking about also extending to the daily after we have a proper model in the monthly value, so that we can actually continue to our different modeling approaches. But of course, I mean, daily predictions are much logical in that sense.
But
So
there
yeah,
will be
it's-
even much more zero inflated. So, and much more, there will be much more, the
Yeah,
monthly
also-
precipitation is relatively systematic. So you know, you can model it a bit easier for now. The second question on the,
for the hydrological enforcing. It can be done actually, but I think I'm not sure in a global scale with hydrological forcing and also including other models computationally. I'm not sure how heavy it is, but of course, yeah, that can be definitely tried for that sense. Yeah.
Luca question, yes? Then we stop for coffee.
The first question I had was the same of Paolo. Actually, we have worked together, but the problem I see here is that 1 kilometer, when you say 1 kilometer, please have a look at the pattern at 1 kilometer and please make a comparison with kind of actual 1 kilometer data, because otherwise we claim 1 kilometer, but 1 kilometer is not, because to 20,000 stations for the global is nothing. In Italy, we have 3,000, just Italy. In Germany, probably, I don't know, 15,000. So that's looking really at the spatial pattern at 1 kilometer would be really, at least scientifically, the real added value of the product. I would be very curious. Paul is talking about forcing with the hydrological model. If you stuck with monthly, it's not possible. But if you move to daily, very happy also to collaborate on that.
Yeah, thank you, Luca, for this. You're definitely right, actually. So that's why we hesitated to write 1 kilometer, because that's why I had 1 to 5 kilometer resolution, because definitely even with the test data set we spared, it's not impossible to validate the real resolution we have after the modeling. So that's why for that we need local data set that are more dense, like you said in Italy, or we have a couple of other data sets that we didn't include it in the modeling. But of course, it's also subject to another thing. I mean, we can also include lots of local data sets into the global model to increase at least the special pattern in some certain regions. But of course, we also need another data set that is dense enough to validate at how much scale we could actually downscale or not. So you are definitely right. The resolution is still unknown, but
We will look at
yeah,
we have to look at the
we
pattern.
have to
That's
look at the pattern,
that's
yeah.
the key.
Yeah.
Okay.
We are very happy to collaborate on that.
Sure.
We have a quite
Great.
experience.
Yeah.